Yeah.
Let's just talk a little bit while people still wondering. So last time I had a splitting headache, and I think it showed because that wasn't my greatest lecture. Hopefully the notes are better. Obviously, we've been working on pretty theoretical stuff. Right? I mean, the QR factorization stuff and all that was kind of practical because it helped us come up with algorithms for solving linear least squares problem, this business of conditioning, and now stability. It's a little bit more theoretical, right? It's actually very important work. It's really classic work. It's stuff that was done in the 1960s that, for the most part, people don't really do much anymore. I wrote what I thought was, I was co-author on what I thought was a pretty darn amazing result, which essentially, we can, the notes that I'm working on right now for you are based on a paper that we published about 5 or 6 years ago that came out of the dissertation of a student of mine, Paolo Biantonesi. And I found the results so earth-shaking that I strongly recommended he not put it in his dissertation. Okay, and the reason for that is that if the best result you ever have in your career was in your dissertation, people will always say he's doing great stuff, but it's not as good as his dissertation was. So I strongly recommend that don't do this, okay? And he put it in anyway, and then we wrote a wonderful paper about it. And in 5 years, it's gotten one citation, and that citation is from a paper that I wrote. Okay? Which goes to show that, yes, what we did, I think, was really, really significant, but it doesn't seem the world particularly cares. And sometimes that happens, right? So stability analysis is just really ingrained in the subject. People have learned that certain techniques are numerically stable, and therefore they kind of stick with them. Those are the algorithms that are based on unitary matrices, because multiplication with a unitary matrix doesn't amplify error. And for the rest, people kind of avoid the whole subject because it's just nasty. Right? It's just really nasty. But it's not that nasty. Okay? It can be made pretty systematic. And so what I've been doing is I've been trying to rewrite this paper that we wrote a few years ago into something that's a little bit lower level. Actually, that paper itself was kind of funny because when we first submitted it to the SIAM Journal of Matrix Analysis and Applications, I think is what it's called. It's the top journal, top journal in the area by SciMax. We wrote a 35-page paper that had exercises in it. And it came back saying, well, this may be a good result, but get rid of the exercises. As a matter of fact, take it down from 35 pages to 20 pages. To which we then responded and said, well, yeah, but the way we've written it as 35 pages plus exercises, an undergraduate can understand it. And the answer came back from the editor saying, well, that's very nice, but we're satisfied if the 5 experts in the world understand it. So we cut it down to 20 pages, which means that now nobody understands the paper. And, anyway, we just refer everybody to the technical report that has all the exercises in it. So anyway, you'll get that paper. Hopefully you'll understand it. We're going to start with a slightly simplified version. The paper pretty quickly dives into backward error analysis of and solution of triangular systems, and then of LU factorization. Given that we haven't yet talked about algorithms for solving triangular matrices, nor algorithms for performing an LU factorization, we're going to not quite dive into that yet. We'll kind of work these results in as we go along, and we'll just focus on a little bit more the principles of what's going on. Okay? Any questions? So the homework, I gather that quite a few of you have exams today and tomorrow. So the homework is due on Thursday. We delayed that a little bit. In principle, we have an exam a week from Tuesday. And I'm leaning towards changing that into a take-home exam. Because,
I'll lean with you on that.
well, but strictly speaking, on the syllabus, it says that we're going to have an in-class exam. So, you know, if you really, so it's not that I want to give you a longer exam. It's not that I want to give you a harder exam. It's that I, on the one hand, realized that we jumped into pretty advanced topics pretty quickly in this class. And that simply may take a little bit longer to mature, and therefore having it as a take-home exam will help. And the second thing is I would like for it to be a more meaningful exam. So I can ask not necessarily harder questions, but I can ask, you know, sort of staged questions that lead you into understanding better on a take-home exam, which is why I'm leaning that way. But, so the way we would want to do this is I would hand this out probably a week from Tuesday and then have it due a week later, not because it will take a week.
A week from today or 2 weeks from today?
A week from...
Today's Tuesday.
We had 2 weeks from now, I think, is when we were supposed to have our exam, right?
Okay.
Is that, or was it Thursday? 14th?
Yeah, 14th.
And today is the 7th?
Yeah.
So the exam was supposed to be the 14th already?
Yeah.
16th, right? Okay, so on Thursday. So let's hand it out on Thursday and have it be due on Tuesday. Is that okay?
Wait, this Thursday or next Thursday?
A week from Thursday.
Okay.
Okay, a week from Thursday I'll hand it out. It'll be due 2 weeks from today. Okay? And the rules will be that you must work on it on your own, but you are allowed to use notes. You are allowed to come to me. You're allowed to go to Kai. But, you know, this is a, what's called a diversity class. Only in Texas would diversity be taking linear algebra, right? Anyway, this is a diversity class, which means it has to be rigorously graded, which means I have to make sure that you actually do the exam yourself. So there's no collaboration on that exam. Okay? And we'll go over the rules more carefully when it's handed out. Fair enough? Okay, so we'll do it that way. Unless somebody protests, okay? I mean, things are in a certain way in the syllabus, and you know, if I start changing rules, people should be allowed to protest. Okay, let's go on. We're talking about numerical stability. Okay? Now, what is numerical stability? Stability is the notion that in the presence of round-off error, you cannot expect to get the correct answer. For example, you may not even be able to store the correct answer because you will have to represent it as a floating point number. And therefore, moreover, it could be the case that you have an ill-conditioned problem, which means that any kind of small error may greatly change the final result. And therefore, all we can strive for is what's known as a numerically stable algorithm or implementation, by which we mean that you get the exact answer to a slightly changed problem. Okay, and if you can prove that you always get the exact answer to a slightly changed problem, in other words, whatever error you get can always be attributed to a slight change in the input data, or is no worse than a slight change in the input data, then you have an algorithm that's about as good as it gets. And the analysis that shows that is known as a backward error analysis. That was, pioneered in the 1950s and 1960s. So the notion of now, I'm going to hand you out notes, and then I'm going to hand you a pointer to the actual technical report on which this journal paper that I talked about was based. The notes that I'm putting together now are sort of a more gentle introduction. The paper itself should then be understandable. And to sort of put things in perspective for those who are in computer science, what Dijkstra wanted us to do was to systematically create correct programs. The idea being that you prove the correctness of the program hand in hand with the correctness, hand in hand with deriving the program in the first place. And this is something that is part of our research. We have made practical. We haven't really talked about that yet. What the paper that I'm going to point you to does is to say, well, once you have a correct algorithm, correct in the sense if no error were to happen during the computation, then you would like to come up with this backward error analysis, and what we essentially do is we give a very systematic way of deriving this backward error analysis for an arbitrary operation. So we make the process of coming up with a backward error analysis very systematic, which is what we as computer scientists do. Okay, we look at something, we try to identify the system behind it, and we try to hopefully even automate it. So in principle, one should be able to write a theorem prover that will then automatically come up with the error analysis. Okay, that would be the ideal. But given that nobody pays any attention to the technique, perhaps this would be a wonderful dissertation that also nobody would pay any attention to, and that, of course, is a little discouraging. But let's get back to the point. Now, this contrasts sort of with the more usual way in which stability analysis is taught, which is you kind of have a bag full of tricks, and if you remember the right trick, then magically the result comes out, which, I poke fun of mathematicians and I poke fun of engineers. My apologies to the mathematicians and engineers in the audience, but, I sort of say, well, mathematicians seem to take great delight in coming up with an answer and then giving the most obscure possible proof for it, because after all, you look so much smarter then, right? And again, my apologies, I have a PhD in mathematics myself, I just offended myself, don't pay too much attention. Okay, let's dive in. Okay, so the whole point of backward error analysis is you have a function that goes from a domain. Okay. I was organized today and I brought pens, I think. Yes, I did.
You can make a calendar with a vending machine where you stick a quarter in and get out a...
That would not be bad.
Just throw that in the washing machine.
Oh, well, maybe not. Okay. We have a domain that the function f takes into a range. And the idea is that if you plug in an input x, out comes f of x. F takes this across. And what you actually do is you have a program into which you put input x, and that program instead computes an approximation of the result. And what we need to do is we need to be able to show that there's some nearby input, x plus delta x, that under the original function f gives this exact same result. And that's the purpose of the game. So, we talked about floating point numbers last time. And what did we notice? What we noticed was that if you took a real valued x and you represented this as a floating point number, which we're also going to use square brackets to denote, then out becomes something that we're going to call x check, or check x. X check, check x, whatever. And the idea is that we're going to need to show, well, it sure would be nice if we could show that x check is actually x plus some changed value x like that. Okay? And that's exactly what we saw. What we saw was that you represented as in essentially as a well, what do you call it? Engineering implementation, whatever. And then you take part of your mantissa, you throw it away or you round it. And the bottom line was that when you store it, you could say that the absolute value of the difference between these was bounded by some number, and that number we gave a name, and that was the unit round off. Okay? And if you're using single precision arithmetic, you get 10 to the minus 8 approximately for that, and otherwise you get 10 to the minus 14. But the important thing here is that storing x as a floating point number is storing exactly f x check, but x check. So this, think of this. Let's talk this through. You would have liked to have stored x, right? What we're doing is we're doing an approximation of the storing of x. So f of x here is equal to store x. The approximate storing of x, the actual implementation of storing x, is this function that changes it into a floating point number, right? And what we notice is that that actually is equal to x plus some change in x, where the absolute value of that is less than or equal to the unit round off. Okay. But this, of course, is just store x plus delta x, right? Which means that we're actually storing exactly a number that was close to the original number that we wanted to store. And as a result, storing a number is a numerically stable function. Or algorithm, is what I should say. Storing a number as a floating point number is a numerically stable operator, which is pretty good because obviously if just storing a number wasn't numerically stable, we probably could all just go home, right? Cancel class, no point in having a midterm, none of this stuff is useful. All right, now, so what we need to do, okay, another thing that we do in computer science and mathematics is we come up with a model of computation so that we can theoretically analyze what's going on. Okay. So here is the model of computation. So we're going to call this the standard model of computation. Okay? And here I'm just following notation that was introduced by someone who's considered one of the gurus of stability analysis, Nick Hyam, who's a professor in the University of Manchester. And so what's the standard model of computation? Well, if you have a chi and a psi that are real numbers, what do we start with? Well, we start with, let me make sure I use the same symbols here. We start with the operations plus, minus, multiplication, and division, right? That's pretty much what we start with. And if you do xi plus chi plus psi, and you then take that number. Okay, side tour. Let's say that we have some kind of expression. Okay? If I put square brackets around this, what I mean is when you do this arithmetic in your computer, it's the floating point result of what comes out of it. Okay? So what does that mean? It means that each of the individual operands is rounded because you end up storing it as a floating point number. Okay, so that's just converting each of those to floating point numbers. And then, in the order in which the computation happened, you perform the computation as in floating point arithmetic. And you would do so, in some order. So it may be, that's the order in which the computation happens. So anytime I put square brackets around it, what it means is do every sub-operation in the floating points with the floating point arithmetic that your computer would perform, and then end up with the number as your computer would have then computed it with floating point arithmetic. Got my point? Here, of course, we're only doing one floating point operation. And actually, I need to be a little careful. I'm going to start with two floating point operations, and I'm going to denote the set of all floating point numbers as the set F. Okay? So, what this here says is, we start with a chi that's already stored in your computer. We start with a psi that's already stored in the computer. We now perform some operation where this operation is one of our most basic floating point operations, or operations that we can perform, arithmetic operations. And what we would like to now say is, what comes out of this? Well, what comes out of this, it'd be great if the exact result came out of this, right? Wonderful, hooray, no error. Yeah, we can also go home, because clearly numerical stability analysis is going to be very simple. It's just going to be real analysis of real arithmetic. Not quite. Instead, you get, well, if we got this come out, that would be good too, right? Because that's the same. But what actually happens is that a slight perturbation happens, where the absolute value of epsilon is less than or equal to this unit round. So what that really says is, this is the way to think of it. When you think of floating point arithmetic with two floating point numbers, the result of doing the basic arithmetic operations is the same as if you did the operation exactly with these floating point numbers. Okay. This would be the exact result. And then you took the result of that and you stored it. And the only place where actually error happens is in storing the result. Okay, so think of a floating point unit in your computer. Okay. What essentially we're saying is the floating point unit merely goes and computes the exact result. But then the result must be stored, and that's where the error happens. Okay? And no error greater than that happens. Now, it may not be exactly the error that happens, but no error greater than that is incurred along the way. Yes?
On the right-hand side, are chi and psi stored as floating points?
Well, since we started as floating point numbers,
okay,
the answer is yes. So these were floating point numbers. This is what the floating point unit would compute. This is then what can be stored because the result is a floating point number.
Got it.
You got it? Now we have a model. What it really says is that a relative error on the order of the machine epsilon, this unit round off, 10 to the minus 8. If you do single precision, 10 to the minus 16. If you do no precision, is incurred. And that's true for any of the basic operations upon which we're going to build everything. You got it? All right. Well, that's a good place to start, right? There is a second model, and that's known as the alternative model of computation. What's the alternative model of computation? Under the same circumstances, it says that this op psi is equal to chi op psi divided by 1 plus epsilon, where this is true. Yes?
In that top right example,
Yeah?
could you just draw the same 1 plus epsilon to the right of all of them?
No, as we will see.
Okay.
Okay, stick with me. What we're going to do is we're going to analyze dot product where a lot of this kind of stuff is going to happen, and then everything will become clear. Okay? Good. All right. And it turns out that if you pick and choose which, now this epsilon, by the way, is not that epsilon. But if you cleverly pick and choose which one you use when, results just plop out much nicer than if you only stuck with that one. Okay? How are these two related? Let's see if there are any really sharp people today. What's the Taylor series expansion of 1 over 1 plus epsilon? Hmm? 1 minus epsilon plus epsilon squared minus epsilon cubed, etc., right? So clearly, if epsilon is very small, this is approximately 1 plus minus epsilon, right? Which, if epsilon in absolute value is less than the unit round off, minus epsilon is also less than that. And what you can approximately do is take this and plug it into that model. So the models are very close, is the point I'm trying to make. Okay. It turns out that if you ever need to divide along the way when you're trying to do analyze some algorithm, for example, if you're analyzing solving with a triangular matrix, then you end up running into a divide by the diagonal element. Then it turns out that for that divide, it's convenient to use this model because you're dividing by, this will then come to the top, and then everything just works out much nicer. Okay? Now, that's where we start. Now, earlier in the semester, we started by saying, look, it's all going to be about slight changes and stuff like that, and therefore we inherently need to be able to talk about how big vectors are, and therefore we introduced norms so that we can talk about closeness of vectors and things like that. We're not going to use that. Okay? It turns out that if you start working with norms, then you're talking about the length of vectors. When you do backward error analysis of operations like the dot product, etc., it turns out that you can actually talk about changes in individual entries as opposed to talking about changes in the whole vector. And obviously, if you can say, well, the computation is equivalent to changing the individual entries, relatively speaking, slightly. That is a much more accurate result than when you lump all of those errors together into, well, in the entire vector, there's some bound on the combined error. Okay, so now, to be able to do that, we need to define a few things. And what are those few things that we want to define? We don't want to get rid of this, we don't want to get rid of that. Here, we'll take care of this. If x is an element of Rn, we're going to define the absolute value of x. And you say, well, we kind of define the absolute value of x, that's where norms came in. Well, that's not the definition we're after. What we're after is if this is the vector x, then the absolute value of x is given by the vector where each element is changed to its absolute value. So it's an element-wise absolute value. And similarly, the absolute value of a matrix is given by the matrix where each element has its absolute value. Okay? And this is going to clean up a whole bunch of notation that we're going to write into. So keep that in mind. And notice that by this definition, if you talk about the absolute value of x being less than the absolute value of y, what we're really saying is that this is true. And therefore, what we're really saying is that for every entry in x and y, this holds. Okay. And notice that that's true for less than or equal to, greater than, less than or equal to, etc. Okay? So this is an element-wise comparison of the entries. Okay? Why this becomes important is going to become clear in just a second. And it turns out that for, sometimes it may become important to bring things back to norms. And it turns out to be the case that if, for example, the absolute value of A is less than or equal to the absolute value of B, then the one norm of A is less than the one norm of B, less than or equal to the infinity norm of A is less than or equal to the infinity norm of B, and the Frobenius norm of A is less than or equal to the Frobenius norm of B. And I noticed that the 2 norm is not on my list, and I didn't go back and rethink why exactly that's the case. But the fact that it's not on the list means that you probably can't assume that. Okay, so pick your norm carefully when you deal with this. Okay.
Is this a norm, the absolute value?
So the absolute value is clearly, is it a norm? Well, let's see. Does it, let's see. To be a norm, oh, it's not a norm. Why is it not a norm? Because a norm maps a vector to a real, and this maps a vector to a vector. Okay? So it cannot be a norm. But good question. I knew it wasn't, I just didn't remember why. Okay. Okay, so now we have a whole bunch of mechanism stuff, okay? Now we're going to roll up our sleeves and things are going to get ugly. Okay? And then we're going to introduce some notation so that things are not quite as ugly. And in this particular area, notation is everything, okay? It just gets horrendously messy unless you have nice notation. And a lot of this notation, again, is straight out of Nick Hyam's book, which I shouldn't say this on camera. I find almost impossible to read myself. But it's got lots of good stuff in it, I'm sure. But you really have to have courage to read it. It's the Bible. It's the document everybody turns to if they want some result. It's the document nobody wants to dig into to double check whether the result is correct, because it's there's a lot of very elegant stuff in there, but there's also stuff that I just can't wrap my head around because I'm notation challenged. Okay, here we go. I think you're going to like this, though. We're going to make things simple. So let's start with a very simple example. We're going to take x and y, and we're going to assume that both of these are floating point vectors, okay? So they're vectors of length 2 that are already stored in our computer. And what we're going to do is we're going to look at the inner product of x and y. Now we can do all of this for complex valued stuff, but you know, just the real stuff is complex enough. So let's not go there. All right? So what is this? This is chi0, chi1, inner product with psi0, psi1, which is equal to chi0, psi0 plus chi1, psi1. Nice enough, right? And we'll say that this result is equal to kappa. Now, kappa check is going to be the result if you do this in floating point arithmetic, okay? Which is equal to chi0 psi0 plus chi1 psi1. But remember that along the way you do a lot of floating point computations. So really, you perform this multiply, you have to store it. You perform this multiply, you have to store it. You perform this addition, you have to store it. Fair enough? Now, what would we like to do? We would like to show, so let's always keep our eye on the 8 ball. We would like to show that, let's see, we don't really need this anymore, so let me erase this. We would like to show that kappa hat is equal to x plus some change in x transpose y. Okay. So in this particular case, delta x would be equal to some vector that would be some small first element and some small second element. Okay? So what does that mean? What we're saying is that kappa check is equal to the exact inner product of a vector that's slightly changed and a vector that's left alone. Okay. That would mean that if we could show that delta x is small, then we could say, oh, it's the exact result of a slightly changed input. That's what we're after. Or we might want to show that we can take the error and we can throw it onto y. Or we may say, no, that's not going to work, but we can throw a little bit onto x and we can throw a little bit onto y. Okay? Then it's still the exact result of slightly changed vectors. With slightly changed vectors. And sometimes it's actually not a backward error that you want, sometimes you want to do what's known as a forward error. The forward error would say that no. Kappa check is actually equal to this plus some change in the result. So there we're saying it's actually the result that hopefully is small. You got my drift? And it turns out that sometimes you will want this result, sometimes you'll want this result, sometimes you'll want that result, and sometimes you want that result. And therefore, having what we would call an inventory of error results for the dot product is convenient, because then when you later end up with an algorithm that requires a dot product, you can pick and choose which one you want to use, because you may need a different result in the setting of a different algorithm. Okay, we'll get to that as we move on. Okay, now we're going to analyze this in such a way that we can get all of these results easily. Okay? Which unfortunately means that I'm going to go against what I said I was going to do. I'm going to pull a trick. Okay? And I said, no. We're not going to pull tricks. We're going to have a systematic way of getting there. Well, you could get there systematically, but this trick is so beautiful. Let's work on it. Okay? Sometimes the mathematician in me takes over. All right. So here's the idea. We know that this is equal to chi0 psi 0 chi1 psi 1. And notice that when you perform this here, you incur an error. And we'll call it an error that was due to a multiplication, and we'll put a superscript on it, because we're going to have lots of errors that are going to pop up. We're going to want to track all of them, and we're going to want to distinguish them. All right? Similarly, an error happened when you did this. And we'll put a superscript 1 on that. Okay, so that just accounts for these red brackets. And then in the end, you had to take the result of that and add them together, and that incurred yet another error, which we'll put up as such. And notice that all of these are all in absolute value less than or equal to our unit round-off because of our standard computational model. Yes?
Was there a particular reason why you chose the superscript 1 for the plus?
It'll become clear when we have more vectors, longer vectors.
Okay.
Okay, so yes, there was sanity behind this. No, there was reason behind this sanity. Insanity, whatever. The choice. All right? You get my point? And notice that I should have put this farther over. You can manipulate this a little bit, and you can then distribute this, and you get chi0 psi 0 times 1 plus epsilon star 0 times 1 plus epsilon plus 1 plus chi1 psi 1 times 1 plus epsilon star 1 times 1 plus epsilon plus 1. Okay, and you're starting to see that this one here is getting to be within reason, right? Because you could multiply all of this out, you could pull out a psi 1, and then you could take all of the epsilons added together times psi 1 and make that your, well, let's go on. Sorry. Hopefully you have written this down somewhere, so I don't have to. Well, actually, we're going to only use that, so I'm going to erase this. There we go. Okay. Notice that we can write all of this as chi 0, chi 1 transpose times psi 0 times 1 plus epsilon star 0 times 1 plus epsilon plus 1 psi 1 times 1 plus epsilon star 0 1 plus epsilon plus 1. Right? And then what you can, now it's really starting to look like this one is within reach, right? And it's not that hard to see, sorry, this one is within reach, and it's not that hard to see that this one is within reach too, because we could always have pulled this all over to chi 0 instead and left psi 0 alone. Right? And here comes the trick. The most beautiful way to write this is as chi 0, chi 1 transpose times the matrix 1 plus psi star 0, 1 plus psi plus 1, 0, 0, 1 plus epsilon star 1, 1 plus epsilon plus 1, times psi 0, psi 1. Okay, so you can write this as x times some matrix, let's call it D, times y. Okay. Can you imagine how ugly this is going to get if we have vectors of length n? You can sort of imagine that something similar like this is going to come out. But this is going to be horrendous, right? Things aren't going to fit on your page. Things are going to be really ugly for me to grade. Which is really what I care about, right? Yes?
Is it acceptable to just set epsilon to its maximum value for a boundary?
So we're going to do something similar to that.
Okay.
It turns out that these kinds of expressions that are just multiples of many 1 plus epsilons are going to come up a lot. Okay? And notice that if you have 1 plus epsilon 0 times 1 plus epsilon 1, then that's really 1 plus epsilon 0 epsilon 1, no, 1 plus epsilon 0 plus epsilon 1 plus epsilon 0 epsilon 1, etc., right? And you could say, well, this is itself a small number, right? And we could give it a name. We could give it the name theta 0, theta 2. Okay? As a matter of fact, if we have the product of a whole bunch of these, what we can do is we can simply say, we'll call that 1 plus theta n, where the n simply says there are n of these being multiplied together. Okay? And if each of the epsilon i's is less than or equal to the unit round-off, then you can prove that the absolute value of theta n is bounded by something approximately, well, actually exactly n times the unit round-off divided by 1 plus n times the unit round-off. Okay, which we're going to call gamma sub n. So we're just going to give it a name. Now, a bunch of comments. First of all, this is roughly n n times the unit round off, right? I mean, here, if you ignore this term, this is roughly 1 plus 2 times the unit round off, because this here will be bounded by 2 times the unit round off in absolute value, right? So this is roughly n times the unit round off. Because u is roughly 10 to the minus 16th, it's going to be a long time before this doesn't look like a 1, right? Eventually things can get out of hand, but things will have to be very careful. So the point is, having a bunch of these multiplied together is roughly the same as 1 plus n times the unit round off, in nature. You get it? Now, notice here, it would be tempting to say that this here we're going to replace by 1 plus theta 2, because it's 2 of them multiplied together. And we'll take this and we'll replace it by 1 plus theta 2. Boy, would life be a lot more beautiful then, right? What's wrong with that picture?
Your epsilon stars are different epsilons.
Ah, our epsilons are different epsilons here in general. In this case, only this epsilon is different from that epsilon, and therefore this theta 2 is different from that theta 2. Dangerous, right? And guess what? Life becomes so much easier if we're sloppy like this. We're going to do it anyway. Okay? Well, what does this mean? What this means is that theta 2 is now not actually a number. It's not actually a variable. It is a quantification of how many of these were lumped together. Okay? So no longer can you start factoring them out because the theta may be a different theta. And as long as you keep that in mind, you're okay. Okay? As long as you keep in mind that not all thetas are created equal. They're bounded equal, but they're not created equal. All right? Then everything is okay. Because then everything just falls out so much prettier. Because then we can take all of this and write it as chi 0, chi 1 transpose times the identity plus theta 2 on the diagonal times psi 0, psi 1. And this quantity here then we're going to call the special matrix, this quantity here we're going to call the special matrix sigma 2. Just this part of it. Okay? And notice that then all of a sudden all of these fall out because for the specific case where the vector is of length 2, this here is just x plus sigma times x, sigma 2 times x, transpose times y. Because you can take all of this and you can write it as x transpose times 1 plus sigma 2, which you can write as 1 plus sigma 2 times x transpose. We're keeping in mind that this is a diagonal matrix, and therefore its transpose is itself. And then you can write that as x plus sigma 2 times x. You got it? Similarly, this one we can write as x transpose times sigma 2y. Sorry, y plus. This here we can write, anyway, you could always take your diagonal matrix and split it apart, right? And that would get ugly, so let's skip it. And then this one we could write as x transpose x, x transpose y, plus things get ugly, right? I guess plus x transpose sigma 2y. And then this. So this would be your delta x. This would be your delta y. This would be your delta kappa. You with me? And now the only thing we need to do is bound them. And notice that if you take chi 0 if you look at this right here, sigma 2 times x would be equal to theta 2, 0, 0 times chi 0, chi 1, which is just theta 2 times chi 0, theta 2 times chi 1. If we take the absolute value of this, which of course would be the absolute value of delta x, then you would do this, which would be this, which would be the vector theta 2 x chi 0, theta 2 chi 1, which would be equal to the absolute value of theta 2 times the vector chi 0, chi 1, which would be equal to theta 2, by the way, is always positive, so we don't need to put an absolute value around it. And this would be the absolute value of x. And notice that theta 2 in absolute value is bounded by this gamma 2, which we defined as n times the unit round off divided by 1 plus n times the unit round off. Okay, the point being, the change in x is actually a small change of x. Is the point. Et cetera, et cetera. Did I make a mistake somewhere?
Sorry.
She always catches me.
Why theta 2 always should be positive?
Theta 2 should always be positive. Oh, it should not be. No, you're right. I did not make that assumption. We'll leave it in. Yes?
Are theta 2s different in the best we can't factor them out? Or
Yeah, I was a little okay, so fine. I should have done this differently. I should have said is equal to theta 2 times chi 0, theta 2 times chi 1, which then is bounded by
The larger one.
let's see, gamma n times chi 0, gamma n times chi 1, right? And then I could have pulled the gamma n out instead. Is that better? Okay, so this goes to show, this is nitpicky, isn't it? You gotta really be thinking all along. Hopefully I did it right in my notes. Let's see, what did I do in my notes? Oh, I didn't even get to that. I did the general case instead. In the general case, I was a lot more careful. Yes?
So when you define kappa graph in the third line on the right hand side?
This?
Yeah, so when you store x, there would be some error in the floating point storage.
Correct.
As well.
So notice that I said, let's start by assuming that x and y are already floating point numbers. Otherwise, I would have had to put brackets around that as well. Absolutely. Okay, so there's a difference between the error you get if you started with x and y outside of your computer, plugged them in, did the dot product, and then like to the result, versus you already have vectors in the computer and now you do something with it. Now the dot product often comes up in the setting of other algorithms, and when they come up in the setting of other algorithms, the numbers are already in the computer, and that's why this is a better place to start, from the point of view of creating building blocks. But that's a very good comment. Okay, you sort of kind of see what we're after here. Are we ready to go on and look at the general dot product? Scary stuff. All right, let's go. We might want to keep that result up. We might want to keep this result up. Let's erase this. What if we have x and y vectors of length n, where the vectors start already as floating point numbers? And we now look at x transpose y. Okay? Then notice that if the exact result is kappa, then the computed result, well, of course, it depends on the order in which you actually do the additions, right? But let's just say that we're doing it in the natural order, where you do chi0 psi0 plus chi1 psi1 plus dot 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 plus chi n minus 1 psi n minus 1, where I'm purposely giving myself a lot of room here, okay? Now, we do this, well, we always do the multiplications first, and whether we do this all at once or one at a time, or whether we pop all over the place, the error that we're going to get is always the same, right? It's going to be 1 plus epsilon star 0 here, 1 plus epsilon star 1 here, and so forth, right? Fair enough. But now things get a little bit more complex, because if we do our computation from left to right, we end up with another error here, right? That's the one we saw before. Right? And then we end up with another error here. And we get a dot, dot, dot. And we get another error eventually over here when the final result gets added in. And now you can sort of see why we have these superscripts in some organized fashion. Okay? Now notice that there's an error here, but then that one gets hit by this addition, another error, and then another one here, and another one here. So you really get chi0 psi0 times 1 plus epsilon star 0 times 1 plus epsilon plus 1 through 1 plus epsilon plus n minus 1. Right? And then you get plus psi1, sorry, chi1 psi1, and there you get the error from the multiplication. And then lo and behold, you get the exact same number. Wait, this should have been a 0 here. No, 1 here is fine. you get your 1 plus epsilon star, plus n through 1 plus epsilon plus n minus 1. But then you actually end up with fewer, right? You get a chi 2 psi 2. You get a 1 plus epsilon star 2 times 1 plus epsilon plus 2, and then you get, okay? The fact being that here, how many are we multiplying together? N, so we should get a 1 plus theta n here, right? And then here we should get a 1 plus theta n here. But this one here becomes a 1 plus theta n minus 1, and the last term will only have 2 of them. Right? So, it is not hard to see that this whole result is equal to chi 0, chi 1 through chi n minus 1 transpose times a diagonal matrix that's I plus the matrix theta n minus 1 down to theta 2, with 0 sitting here, times psi 0, psi 1 through psi n minus 1. Okay? It's just a direct extension of what we analyzed before. And then you can pull your tricks of either making your delta y this times that, or making your delta x this times that, or taking this time transpose that times that and making that your kappa, your delta kappa, etc., etc., etc. Okay? So, what does this mean? Well, this means there's a whole bunch of little details. All of this, by the way, is in the notes. Let me just go directly to the results, which is what we need. So, if you analyze all of this and say where the absolute value of the change in x is bounded by gamma n times x. Now, where does that come from? Okay, this means that you take this times that to be the delta x vector. And notice that if you accept that theta n is greater than or equal to theta n minus 1, etc. in magnitude, then it's not that, and each of these is bounded by this magical gamma sub n, then it's not hard to see that each of the individual entries is bounded by gamma n times, well, you get the point. Right? Let's just leave it at that, okay? The details are in there. And then here you would say where the change in y is bounded by gamma n times y. So notice that there's a small relative change in y in the input, which means it's numerically stable. And then here you can say where the change in kappa is bounded by, this one is a little bit more complex, gamma n times That's interesting. So notice that this is a vector of the absolute values of the elements of x. This is a vector of the absolute values of the elements of y. You take their inner product and then magnify it by gamma n.
This is about for the last case.
Excuse me?
I mean, this is about for.
Yes, this goes with there. Okay. Sort of kind of get the point? The point is, if you just carefully look at how the elements can change, you can argue that the errors that come up are actually equivalent to changing your input slightly. That was the whole point. Change the input slightly, element by element. Okay? There's a slight change in each individual element. All right? Backward results, forward results. How would you like to do this for your dissertation? I think every other dissertation in numerical analysis in the early 70s, late 60s was something like this. Okay, my dissertation advisor is like a big name in this area. Thank goodness he didn't make me do this, okay? I actually, in writing the notes, I kind of actually enjoy it. But it takes a lot of courage to dive into it, okay? It just takes a lot of courage. Okay. Some people, when you take this class, will end up spending half the semester carefully leading up to a full backward error analysis of LU factorization, okay? And they believe that this builds character, etc. I'm making you suffer through this for parts of lectures, okay? The very, very important results. I don't want to downplay the importance of the results, okay? It's very, very important. But, okay, there are other topics that are worthy of our time as well. All right? So, what can you then do with this? Well, once you know how to do the inner product, what's a natural next step? What kind of operation does the inner product show up? Matrix vector multiplication, right? So what if we wanted to analyze matrix vector multiplication? Well, we could go back to the same kind of analysis, or we could simply say, well, you want to do y is equal to a times x. We want to see what the computed y is. Now we have to choose what algorithm, because we can do an algorithm that does it by rows, or we can do an algorithm that does it by columns. So what if we take the algorithm that does it by rows? Then notice that you simply get the matrix that is the computed value for the inner products for each of the elements. Okay? You can then go over here and say, which of these results might I want to use? Trust me, you want to use this one. So what does that mean? It means that this is equal to A0 plus some delta A0 transpose times X, A1 plus some delta A1 transpose X, and so forth, where we can now put bounds on each of those. Okay? Which you can then write as A0 transpose X, A1 transpose, and so forth, plus delta A0 transpose, actually you can even take this X and multiply it out, delta A1 transpose, and so forth, times X. Okay. And then you can recognize that that's just A times X, that's this here, plus a matrix that will denote as delta A, touching because this is a big matrix of entries, times x. Okay, where this delta A is just created by taking all of these error vectors and making those the rows in the matrix that is now the error matrix. And then you can go over here and see what kind of bounds there exist on the individual rows, and you can use that to find out that the absolute value of delta A is bounded by gamma n times the absolute value of A. Okay, so all of this investment we made in carefully coming up with an error analysis of the dot product, we can now use to quickly come up with an error result for matrix vector multiplication. And notice that what we conclude is that the computed y is equal to A plus delta A times x. It is the exact result with the input, namely the matrix A, slightly changed. Okay. And then you can build that up to come up with an error result for matrix-matrix multiplication. Why? Because we've learned that one way to compute matrix-matrix multiplication is to do a matrix vector multiply for each of the columns. And all of a sudden you can see that this builds. You don't need to analyze each individual algorithm in isolation. Okay, let's call it quits at that. Okay, the rest of the details are in the notes. We'll probably have to spend a little bit more time on this in the next lecture. And I'll announce how